Hey, my name's Dan and I'm an engineer at Edge Impulse. And in this video, I'm going to be just walking through the process of training an impulse so that it can recognize different types of audio. And the thing we're going to be recognizing is whether a faucet or tap is switched on and if water is flowing. So that obviously has a distinctive sound, and we're going to be training a model that lets you distinguish between regular background noise and a faucet with running water. So at the beginning here, you're going to need your STM32 discovery board to be set up with Edge Impulse. So you can follow the instructions in the documentation for that. So I'm going to be starting out by capturing a bit of audio data. So in the UI here, to capture some data, let's just head to Data Acquisition. So this interface lets us capture some audio that we're going to use to train our model. And so just to show it off, I'm going to capture 1 second of audio. We're going to need to label our data. So here, where it prompts for a label name, I'm going to give the label noise to represent background noise. And then I'm going to choose the sensor type built-in microphone. So that means now we're going to capture audio from the STM board's built-in microphone and label it as noise. So the sample length here determines how long that is. So I could do 10 seconds, 1 second. The maximum we can kind of get away with here is 1 minute, because that's how much space we have on the device. We can store about a minute of audio. But for now, just to show it off, I'm going to show you 1 second. So let's click Start Sampling here, and you'll see on the device, the LED will come on to indicate that recording has happened. So it will then take a few moments to upload the sample to the Edge Impulse UI, and we can now see that audio. So let's have a look. Right here, there's a control that we can use to play the audio. And if I play that back, it's just a little speck of background noise. So that's a 1 second sample of noise here. So what we're going to want to do when we're training our model is to capture a lot of audio that represents typical types of sounds that would be heard during operation of our application. So one thing we might want to do is capture just plain background audio. So if we're going to try to recognize the difference between a faucet running and background noise in an apartment, then we want to capture a lot of audio of just the regular background noise of the apartment. So in my apartment, you can hear people driving past, people walking in the next room over. So that audio might also typically include things like conversation or the TV playing, or the sounds of someone cooking, whatever types of sounds might be around as background noise in a typical apartment. So the other type of audio we want is the audio of a faucet running. So we can collect that just by making recordings of the sound of the faucet running, but maybe in a few different contexts. So maybe it could also, in some cases, include the noise of someone washing the dishes or brushing teeth or just moving around, or even with like television or other types of background noise playing. So rather than getting these sort of sterile, perfect samples of like plain silence or the sound of a faucet in perfect isolation, we want to actually collect a bunch of audio that represents real world messy data, the kind of thing that you're going to see in real life, because that's how the model is going to learn to be able to understand what these things sound like in a real life context. So in terms of how much data we want to collect, probably about 10 minutes is a good start for an audio classification task like this, which has 2 different classes. And we want to collect about an equal amount of data for each class. So let's try and collect 5 minutes of data for the background noise and 5 minutes of data for a faucet running. So one thing that I want to point out is the data transmission rate from the Wi-Fi chip on the STM board is pretty low. So it will take a little while to record and upload this audio. So generally what I'd recommend doing is setting a sample length of 60 seconds, which is the maximum we can do. Set up your label and click Start Sampling. And then you'll start capturing that audio. You'll see a countdown while the audio captures here once it gets started. And it'll take a few moments to get started while we erase the flash on the device to make room for the audio. Once it gets started, we will then see the LED light on the device. It'll capture 60 seconds of audio. And then because of the slow Wi-Fi, that's going to take about 6 minutes or so to make its way back to the server. So give about 7 minutes total for each sample that you're going to capture. And eventually we want to capture like 5 samples of background noise and 5 samples of a faucet running. All right, so here's a bunch of audio that I've collected. So I have about 14 minutes total, so a little bit more than we talked about, but the more data, the better generally. So I'll play some of these so you can hear. So this is just one of the noise samples. So you can play it with the raw data control down here. So you can just hear there's some very light background noise. I'll play one of faucet. So here's the sound of a faucet running. And so this audio is actually available in a data set that you can download. So if you don't want to go through the hassle of collecting all this yourself, you can just use those files. However, it is kind of fun to do it yourself, and you'll also learn a little bit more about the workflow. So I definitely recommend trying this out. So now that we've got some data, and we've got, as we can see in our little pie chart here, about 50% noise, 50% faucet, we can start to design our impulse. So to do that, we'll go to Impulse Design. And the first thing to think about when we're talking about audio classification is that we have to classify a certain amount of audio at once. We can't just kind of classify everything at once or classify the whole minute that we collected. That's not necessarily going to work well for most applications. So what we want to do is specify like, hey, we're going to take 1 second of audio at a time and decide whether that has the sound of background noise in it or the sound of a faucet. So what I'm going to do here is set my window size, and that refers to the length of audio that we classify at one time. So I'm going to set that to 1000, so it's a 1 second little window. So the next setting here is the window increase. So if you think about a timeline with audio on it, the window increase basically defines how big a jump there will be each time we take a new window of data from the sample. So I'm going to set that to 100 milliseconds. And that means that we, from a given sample, will take 1 second window of data, and then we move that window forward 100 milliseconds and take another window of data. And we'll keep doing that until we've got a bunch of different windows of data from the sample. So the next thing I'm going to do is add a processing block. And the block I'm going to add here is the MFCC block. So the MFCC block basically takes audio, which is a very kind of redundant form of data, raw audio. It contains a lot of information that we don't particularly need to feed into our neural network. And it kind of distills that down into a form that's a little bit less redundant and easier for a neural network to work with. So we'll show you how that works in a minute. And then the final thing we're going to add is this learning block. So I'm going to choose the neural network learning block, and we're going to use a convolutional neural network to learn to recognize these two different types of audio that we've got. So once those are added, I can save the impulse. And you'll notice we've got a couple new entries on our menu on the left-hand side. So let's click on MFCC here and see what this is all about. So on the MFCC page, we can configure our MFCC block. And basically what the MFCC block does is it runs a fast Fourier transform across the audio input and basically breaks it down from a raw audio signal into a bunch of frequency buckets over time. So you can see that here in this diagram. So basically what that shows is every vertical column is a block of time, and every horizontal is a frequency bucket. And so the audio is being broken down into this spectrogram, which represents sort of visually and also in terms of a matrix of numbers, the frequency domain of the audio. So We're not going to actually change any of the parameters here because the default parameters that are in Edge Impulse work really well for this task. But you can kind of see how we have our raw audio here, and we're able to jump around to different windows within it, so different 1 second windows, and see how the result of the MFCC changes based on where we are. So this is noise here. So let's have a look at a sample of Faucet and see if it looks visibly different. So yeah, the Faucet noise looks very different visibly. And this is the type of difference that our neural network is going to be able to pick up on. So now that we've had a look at how this works, the next thing we want to do is generate features. So if we click up here, what we're going to do is actually take these windows from all of our training data, and we're going to run each window through the MFCC, and we're going to come up with a whole set of MFCC outputs that we will then use to train our network. So if I click generate features, we get a log here of how this is going, and it will take a little time because we have a fairly large amount of data. It takes some time to do all of this processing. So first of all, it's going to create the windows from the files, and once it's done with that, it's going to start calculating these MFCCs for each of them. So there are going to be 8,600 or so windows, so this is going to take a little bit of time. So once all of our features have been created, we're ready to go on to the next tab. So the next tab here is the neural network classifier. So this is the exciting part. This is where the neural network is defined and where we will train it on our MFCC inputs. So a neural network is made up of a bunch of different layers that successively transform an input from its raw initial state into the output that we want. And in this case, the output we want is a set of probabilities, one for each class. So we'll have one number that says the probability that the audio we heard was background noise, and another probability that says whether the audio we heard was a faucet running. And so those two probability numbers will sum to 1, and that will be the output of our model, is these two separate numbers that we can use to decide whether we think background noise or a faucet was heard. So in Edge Impulse, you can actually define your own neural network exactly how you like it. You can do that within the UI here, and you can also use more advanced tools like Keras, or even edit the impulse as an IPython notebook. So if you are an ML engineer or you have ML engineers on your team, they can use familiar tools to work with the model that's going to end up in your impulse. The really cool thing though is that the network that is built in as the default in Edge Impulse is going to work great for our task. So we're not going to do much to worry about this for now. But this is the kind of thing you can tweak to make a smaller model that runs faster or fits in less memory on devices. You can use different types of model architecture that are good for different tasks. It just happens that the default here works really well for what we're doing. So the other stuff that we want to play with on this page are the number of training cycles. So this is how many times the training data is run through the network in the training process. And so training for machine learning, the way it works is you basically run data through the network, comes up with an answer, and then you look at how right or wrong the answer is and adjust all of the internal parameters of the network a little bit so that it's slightly more correct next time. And you do that for a bunch of different pieces of data. And in this case, right now, we're going to be running through the entire set of data 300 times. So just through some trial and error, I figured out that that's what's going to work well for this model. When you come and do this yourself, you can play with this training cycles number to try and get a number that works well for you. So the other thing that we want to change is our minimum confidence rating. So by default, we're saying we want there to be an 80% probability that the classification goes one way or another. And that's how we'll consider whether it was a confident classification. So if we're getting a number that says it's 0.9 probability that the faucet was detected, then we'll consider that confident. If it was 0.6, then we wouldn't consider it confident enough. And so we're kind of saying, like, we need you to have a certain degree of confidence before we're going to actually consider this an answer one way or another. So by default, this is 80. or 0.8, sorry. So I'm going to reduce that to 0.7 just because we don't need to be super confident because we're only classifying whether water is running or not. So the next thing to do is just start training. So if I click this button here, we'll see that in the cloud, basically this model is being trained. And it's going to take a while. Training neural networks takes an amount of time that is linear to the amount of data that they are being trained with. We have a fair amount of data, and so it's going to take a little while, but you can see these stats scrolling past. These will be useful to think about as you look at how your network is performing and how you can improve it. But for now, I'm going to just skip ahead to the point that the network is trained. Cool, so now our network has finished training, we get this extra panel at the bottom, which gives us some information about its performance. So it's worth noting here, when the network is trained, we actually are setting aside 20% of the data to do something called validation. So validation basically is when you use some data that the network was not trained on because you set it aside in order to profile the network and see whether it is accurate or not. So the validation data is fed through the network, and we look at the output and compare that to the ground truth, which is like the actual accurate label of the data, and we decide whether it matches up. And so we can see from our last training performance section here that the accuracy is really high for this model, so it's 99%. So that means for 99% of windows, the classification was correct. And you can see that in our confusion matrix here. So this is just a little table where each row corresponds to a certain class and each column corresponds to a certain class. And the number is the number of classifications that fell into this intersection. So in this case, when a faucet is the label, then faucet was the prediction 839 times. And when noise was the label, faucet was the prediction 7 times. So that means our network got it wrong and confused the faucet and noise a few times, but it actually did really well. It only misclassified 18 different windows. So that's looking like very good performance. In fact, sort of looks suspiciously good, like we might have a little bit of overfitting, which is when the network learns to perfectly perform or memorize the training data, and it then doesn't generalize to real world data very well. So it's very important that the next thing we do is test our model and see how it performs on real world data. So to do that, I'm going to head to the live classification tab. And so this lets us connect again to our device. So I've got it sitting here, and we can have it capture some more data. So let's have it capture 1 second of data. So I'm going to click this button and then be silent for a second so that the audio hopefully counts as background noise. And now we're uploading and the audio is going to be processed and classified. So we'll see the result. Awesome. So in this case, we can see here a summary of the testing results. So because this was just a 1 second clip, we only have one window, and that window is classified as noise. So it looks like our model's performing all right based on this, but this is only one sample size. And so obviously we can't be super confident that our model is doing what we want it to do. And actually it's really important that you test your model on real world data that it hasn't seen during training. So Edge Impulse provides some really cool tooling for that. It has this model testing functionality, which allows you to get a bunch of samples and then evaluate the model's performance based on them. So the way this works is if you go into live classification and capture samples, they will end up in model testing. And you can also go to the data acquisition tab and the test data page, and then capture more samples here, and you can view them and manage them. So what I'm going to do is capture a bunch more samples. The amount of samples I need, really, it should probably be about fourth the size, so like 25% of the size of your regular data set. So I've got roughly 10 minutes of data, say, then maybe I want roughly 2.5 minutes of test data. And it should be representative, so it should cover all the types of background noise and faucets and all the types of audio that you might experience in either of those categories. So maybe I want to capture audio from a few different faucets. Maybe I want to capture audio with a variety of different things going on in the background. And once I've built that data set up, I'll be able to use that to test the robustness of my model. So I'm going to do that now. So 1 second and I will have a lot more data. All right, so now I have a ton of test data to play with. So let's go over to the model testing tab again, and let's see how this goes. So if I select all of these samples, so there's a ton of them here, I can then click Classify Selected, and Edge Impulse will run through and try to classify each of the samples. And if most of the samples classify correctly, so the accuracy is high, then they'll be highlighted green. And if the accuracy is a bit lower, they'll be highlighted in red. So we can see here that overall the accuracy of our model on this real world data is about 85%. And so that's a little bit less than the 90 something percent that we had on our validation set, but that's to be expected. Generally in real world data, you will get slightly less accuracy. But this is looking good. This is a diverse set of data and I'm happy with how it's turned out. So now that we've got a working model, we've tested it and we're happy with the accuracy, we can go on to deploy it. So if we head to the deployment tab here, we've got a couple of options. So we can either output the model as a C library, which can be embedded into whatever project that you're building, or we can actually build a binary for the STM32 board that we can immediately use to just test the model and see how it's working on device and all running on the embedded hardware rather than running in Edge Impulse. So if we go to output format binary and build, the binary will get built containing the model, and we will download that and then we'll be able to transfer it onto our device. So once the binary is downloaded, we can actually just drag it onto the USB device. So if I drag that here, it will then get uploaded onto the device. And once that's finished, we'll be able to test everything out. All right, so now that flashing is complete, we can connect to our device and see the program running. So what we're going to want to do is first connect it via USB, and then we're going to connect to the device itself over a serial connection. So I'm using the program screen to do this. So if I hit enter, I can now enter commands to talk to the device. So if I do AT plus help, this will give a list of all the commands available. And the command that I want to use is AT plus run impulse. And this will run the impulses demo program. So that's going to continually, in a loop, collect a second of data, run inference on it, tell me what the results were, and then do it again. So let's try it. So I'm going to type in AT plus run impulse and then hit enter. So we're going to see a second of audio be collected and inference run. Awesome. So in that case, we've seen that the background noise classified as background noise. So that's a great thing to see. So in order to demonstrate this, I don't have a faucet available here in my office, but I do have a recording of one on my phone, so you can hear that. So let's see if our device is going to classify this correctly. So let's start this faucet sound and run the impulse again. Awesome. So it looks like this is working and it's classifying as a faucet. So you can see that this is a really powerful workflow. You're able to go from Edge Impulse very quickly into having the code running on device and testing it out in the real world. So it's super exciting. So I hope you've enjoyed this quick tutorial, and if you're planning on trying this yourself, there's actually a full written tutorial which goes into a lot more detail about how all of this works. So you can find that here on the Edge Impulse docs, and the link will be in the YouTube description below. Thank you so much for watching, and I really hope you have fun training your own audio classification models. Cheers!